Good afternoon, everyone. This is Chris Ewing, and it is March 16th, 2019. I am trying to get to my uh, presentation versus my. Okay, so this is a little discussion that I'd like to have with you guys regarding free body diagrams, one of the most important parts of the course. So I'm going to go ahead and get to my slides and so I'm just going to move over to the sections on free body diagrams because these are really important and I want to make sure that you get this done. Um, in order to set up anything with Newton's first or second law, we have to use the free body diagram. The real situation is when you're looking at an object being pulled along a board. For example, the friction experiment that you guys are doing at home during our break. The other thing that I think we need to do is a free body diagram, because that is the diagram, that is the graphical representation of the actual situation that you have. And from there, you can actually start using Newton's first or second law to generate equations, which you can then solve for the unknown variables. So just to start, I have the slide up here called Identifying Forces. And I think this is very important that you pay attention to. So first of all, identify the object of interest. This is the object whose motion you wish to study. Draw a picture of the situation. Show the object of interest in all objects such as ropes, springs, and surfaces that touch it. Draw a closed curve around the object. Only the object of interest is inside the curve. Everything else is outside. And this is important because because remember, Newton's third law actually generates what is called a system. And that's a set of interacting bodies. It could be the table and an IO lab, or it could be a monkey hanging from a branch of a tree. Either way you go, you have to know what object you're working on and what object you need to study the forces for. So locate every point on the boundary of this curve where the other objects touch the object of interest. Again, this is the system situation that you have to pay attention to. Name and label each contact force acting on the object. This is actually kind of important. Name and label each long-range force acting on the object. So let's go ahead and take a look at the symbols that you should use. And again, one thing about physics is it's all about communication. If you start using random symbols, it actually makes the physics harder to understand. So I'm going to go ahead and stress that you should use these symbols in table 4.1 as your general symbols. So the weight is going to be a little w. The tension is going to be T. The normal force is little n. Static and kinetic friction, F sub S and F of K respectively. Drag and thrust. Okay, enough of that. So here's a conceptual example. You remember your friend the bungee jumper? Yes. Here's the bungee jumper has leapt off a bridge and is nearing the bottom of her fall. What forces are being exerted on the bungee jumper? Okay, so I'm going to start by I'm using a program called Mathematica, and I'm going to use that for this particular thing since it allows me to set this up. The sketch is here with the tension and the weight and all that other good stuff. So here's the boundary. You're interested in the bungee jumper, and so now I'm going to do a simplification. I'm going to represent the bungee jumper as a particle. So here we are. Let me just go ahead and get my new graphic in here. There we go. And I'm going to treat my bungee jumper as a point. For now, this is good enough. We're not going to worry so much about rigid body rotation, at least not for a little while. But we will eventually have to deal with that. But for now, a dot is good enough. So now the question is, what forces are acting on the bungee jumper? Well, as the book suggested, draw a boundary around the bungee jumper. So I don't have to do that with my dot, but you should do it if you do an extended picture. Now, once I have it in this form, I can start talking about forces that are acting. So there is a tension, as you can see, of the bungee jumper, of the bungee rope on the jumper. So I'm going to go ahead and draw an arrow, and I know that that tension is acting upward, so I'm going to pull an arrow upward. So here's my arrow. I'm going to call it T. There we go. It's not a very big T. Let's try and make that a little bigger. There we go. That's better. Okay. So there's my T, and I'm placing it right next to my force. The other force that's acting on the bungee jumper is the weight, is her weight. So I'm going to draw another arrow, and I'm going to assume for the moment that that arrow is much bigger than the tension right now. So I'm going to draw it to scale, making it something like this. So there we go, and I'm going to put it right next to the other one, and I'm going to put in the weight, W. There we go. So now I have what is called a free body diagram, but there's one thing missing from it: a coordinate system. So the coordinate system I'm going to draw, and I'm going to make, again, arrows, and I'm going to try and change the color of the arrows to red to indicate that these are not forces, but they are rather the coordinate system itself. So there we are. And let's go ahead and draw the arrow. So I'm going to take, sorry about that, I'm going to take this direction as positive. So there's my positive direction, and I can see my arrow needs to be, come on. Let's just make sure that the arrow setting is right. All right, so here we go. This is my coordinate system, and I'll just make it red. Maybe. I guess not. Okay, sorry about this. So here is my coordinates going positive this way, and I will make my coordinate system positive to the right. So this is plus and this is plus. Let me mark that so we are all clear on it. There's a plus there and a plus there. Okay, so now we've done our first free body diagram. And what I want to remind you of is this is the graphical representation of Newton's first or second law. Now, let's assume for the moment that the bungee jumper is falling so that they're actually heading downward. So my question is, which way is the acceleration? The acceleration, assuming that the bungee jumper is heading down this way, so her acceleration, let me pull up my tools again. The bungee jumper has an acceleration downward. So there we go. That's the acceleration of the bungee jumper. And now we say, okay, how do I describe the motion of the bungee jumper? And the answer is that I'm going to have to use Newton's laws. Now, Newton's laws basically say that the sum of the forces in whatever direction the object's moving is equal to the mass times the acceleration. This you have read. So let's go ahead and do that. Sigma, and I'm not going to use the indices. I don't need those. So I'm going to get rid of them. And the top there too. And I'm going to say Fy, because the bungee jumper is moving in the y direction, is equal to mass of the bungee jumper times A sub y. Why A sub y? Because you're dealing with, you may have to deal with components later on. So I'm just trying to clarify things as much as I can. So there is the sum of the forces equal to MAY. And so now what I can do is the following. I can write an equation based on the graphics that you see here. Based on this graphic, I can write an equation for Newton's second law. Now, I didn't give you any numbers yet, and I didn't give you any variables yet, so I'm just going to leave that alone for the time being, but this is the setup. So now that I have sigma Fy equals MAY, what are the forces acting on the bungee jumper? The tension acting upward is going to be positive. The weight of the bungee jumper is going to be acting downward. So I can write this as an equation that the tension minus the weight equals the mass of the bungee jumper times A sub y. And I can leave that AY off, but I'm going to keep it on there for the moment. And now I did make a mistake. Where's the mistake? The answer is, it is an AY. Which way is the bungee jumper going? Downward. Which way is positive? Upward. So this should be minus MAY. Okay? So now you see this, and I'm just going to put this as a equation for us. So this is my display formula numbered. Let me make this a little bigger. There we go. So here is our free body diagram for the bungee jumper. Let's take a look at another example. So I think this is going to be useful to you. Here is a skier being towed up a snow-covered hill by a tow rope. What forces are acting on the skier? Okay, let's do it. So you see the diagram of the skier, and this is kind of a complicated diagram. We're trying to put the person in and everything like that. But what here is the circle around the person. This is the person. The person is the forces that are being acted on. That is acting on him. Sorry. The circle is around the object of interest that the forces are acting on. So now that we have this diagram, and you should always draw these diagrams whenever you do one of Newton's laws problems. It makes life a little bit easier for you. Let's write the equations. Now, the skier is being towed up a snow-covered hill by a tow rope. What forces are being exerted on the skier? Let us assume for the moment that the skier is being towed up the hill at a constant velocity. Okay? It's not being accelerated. So now that we have the object and we have the forces like the tension here, the weight is acting down this way, and the normal force is going to act this way. The kinetic friction is going to act along the path of motion. So I'm going to again insert another graphic into my sheet, and let us do the diagram for this person. palettes and drawing tools. And so I'm again going to represent the skier as a dot. I'm not going to mess around with trying to draw the skier out an extended body. So here's my skier. And I'm again going to exert a coordinate system on my diagram. So this way is positive, and it's not letting me change colors, so I'm not going to fuss with that. I actually have to edit that out. There is plus and there is plus. And I'll make the text big so that we're all reasonably clear. Plus here, plus here. So now you see that the coordinate system is positive horizontally plus vertically. Am I doing myself a favor? Well, maybe. Let's see. So now let's draw it out. I have a tension acting on the skier, so here's the skier. And I'll just draw an arrow heading up the hill. So there is my arrow, and there's my tension. So let's put it in. Size. So there's tension. Next force. I need to put in a force of gravity. That is acting downward directly. So there's my weight. And just type that in. And now, okay, what else do I have acting on the skier? I have the weight, I have the tension. Now I have also a normal force. So my normal force is going to be here. And that's going to be perpendicular to the surface. That can be tricky sometimes when you're dealing with these angled problems. You need to kind of keep your head about you with that drawing. So here is my normal force. And last but not least, I have a friction force. Now, reminder that the friction force acts opposite to the direction of motion. The direction of motion is given by T. So opposite to T is going to be my friction force. So I'll drag another arrow here. And that is my friction force. And I'll make it smaller because it is going to be smaller in comparison to the tension, because the person is moving in that direction. So again, 16. There's my F of K. Okay, so I have my diagram, right? No, actually, I have a problem. One of the nice things about free body diagrams is to be able to create the components of the vectors that are acting on the body. We have most of them. One that is not formatted correctly is the weight. The other thing that is causing you some trouble is going to be the coordinate system. The coordinate system is going to be very tough to read if we keep it the way it is. So I'm going to have to edit that. And I will go ahead and edit that in the following way. First, let's do the coordinate system. I'm going to angle the vertical so that it is comparable to, it's parallel to the normal force. So there is my vertical, and again, I'm not going to change my mind on this, so I'll just move it over. There that is. Now, since I made my coordinate system plus this way, I'm going to do the same thing with the horizontal. I'm going to change it over from being this way to being parallel with T. So let's go ahead and select it. So the coordinate system, just to explain, is pointing up the plane is positive and perpendicular up to the plane is positive. So now we have that. One other thing that needs to be done. So the next thing that has to be done is we have to fix the weight, because the weight is acting directly downward. We can't make any sense of that. So what I'm going to do is I am going to dash that. Make a dashed arrow, I hope. And I'm going to draw a vector down. That is going to be the component of the weight perpendicular to the plane. Of course, if there is a component perpendicular to the plane, there must also be a component parallel to the plane. Okay, so we'll draw that out. That's going to be, and I'll dash that arrow. Let's see if I can change its color. Oh, I did. Okay. Every little victory. This is going to be the parallel component of the weight. This here, okay, my program is giving me a little bit of grief, but that's okay. I'm going to move this guy. So I'm going to move this guy. So that's the weight. Oh, there we go. Okay, sorry about this. This is W, and I don't have a parallel sign, so I'm going to call it WP. This is the actual weight. Okay, sorry for the adventure, folks. I now have my weight in perpendicular and parallel components, so it matches up with my coordinate system. This is going to make life a little bit easier for us, because now we can basically set up Newton's laws. Let's go ahead and do that. So in here, now that I have all of these diagrams, I am going to write Newton's equations. Now, we assumed that the skier is going up at a constant rate. Therefore, we apply Newton's first law in the form of sigma, and I'll get rid of my indices, F equals 0. Now, this is the vector form. We can't use the vector form because that's too hard. So we're going to go ahead and break it up into components. So in the x direction, or I'll call the parallel direction, what forces are acting on the skier? The answer is I have the tension upward like this. I have the frictional force acting backwards. I have the weight parallel to the plane acting this way. So I can write an equation based on that. And since it's 0, we should be good. So it is t minus w parallel minus f sub k equals 0. So here we are. There is the equations moving up the plane, up and down the plane. Now, what about the perpendicular components? Well, they also have to be there. So I'm going to go ahead and do that. I have two components acting perpendicular to the plane, the normal force and the perpendicular force. So let's write it. N minus W sub P equals 0. So here are two examples of setting up a free body diagram and setting up Newton's first and second law for particular problems. Now, I'm going to, in the next recording, I will do some more specific examples, and you can see some specific examples in Lecture 5 located in your team's lecture notes. Okay, thank you very much.